kind of set it up so these things are oriented nicely along the axes. If I go into the center of mass frame, both of these will probably become diagonal vectors. There will be other things that are nice. This becomes a zero vector. These guys become equal amounts of momentum in opposite directions. But one thing I'll be giving up is knowing the orientation. Well, they'll be going opposite to each other because in the center of mass frame, before the collision, I've got this particularly nice setup with this particle M just sitting here at rest. After the decay, the angle that they're going to but I do know that their momentum still has to add up to zero. So I know that they'll have to be moving in opposite directions. That's the only way their momentum can add up to zero.
Why would they move in opposite directions there if they're moving perpendicular?
You could say the center of mass frame is kind of mark that towards that center of momentum frame.
I think this is exactly where I was looking.
My center, if I have a little billboard here that has the coordinates for my center of momentum frame, that billboard is coasting along in the same direction that original particle was. So relative to that billboard, this guy's going out that way, this guy's going out that way. They're not moving perpendicular to each other because, suppose I was to trace this over time. Here they are right now. Here they are a little bit later. Yeah, this one's ended up here, this one's ended up over here, but the billboard is moving as well, and it's now there. So, relative to that billboard, they are going out in opposite directions. They have to, because that's the only way their momentum can add up to zero.
Okay. I mean, yeah, I agree that their momentum has to add up to zero if we're looking at it for the center mass frame.
Yeah, if I was doing kind of a time-lapse movie, I'd say here we are in the lab frame. My particle's here, and then it's here, and then it's here, and then it would have been here, but it had decayed, and one piece of it is moving straight upward, and the other piece of it's moving straight out that way. And
so,
as time goes on, my ghost of my original particle, which is where I'm putting those coordinate axes, moving along there, these guys.
so graphically though, when we're kind of doing a transformation from our lab frame to our center mass frame, it's not just a rotational.
It's not just right.
Okay. I think I was just treating it like it was a rotational, but that's not the case.
Yeah. If I was kind of trying to say, what do my new displacements look like in that center of mass frame? These are my new displacement vectors, and they're growing longer and longer, but they are in opposite directions.
That makes sense.
Okay, so there are advantages to using the center of mass frame. The fact that these momentum both have the same magnitude, the fact that this guy's standing still. There are disadvantages. The fact that I've introduced a new angle that I don't know, whereas over here I do know the direction of both of those momenta. And finally, just the fact that since our native frame that we're supposed to get the answers in is the lab frame, I have the last step is once I've figured out everything in the center mass frame, I'll need to figure out how to convert back into the lab frame to give answers that I can measure.
Also, when you were saying the center of momentum frame,
which is what I should be saying instead of center of mass, yes.
Oh.
Because center of mass is not exactly well defined. You say, when I say center of mass, am I including, does that mean I'm bumping up the mass for the gamma factors? That's always kind of an ambiguity in relativity. Center of momentum means the frame where the total momentum is zero. And as it turns out, kind of the center of mass of these two particles, in the sense of m1 times its position plus m2 times its position over the total mass, isn't the origin that I want to be tracking. I just want to be kind of defining an origin, defining a coordinate system where all these momentum vectors add up to zero. And the reason why I can kind of carelessly use those interchangeably is with Galilean transforms, that was the same thing. The center of momentum system was the same as a system where your origin is the center of mass of your particles.
But like this.
Yeah, now center of mass is not even as well defined a concept anymore. Center of momentum still is. There's one frame, and then any rotations I wanted to put on top of that. But there's kind of one way the origin can be moving, where the total momentum of the particles, both before the collision and after the collision, add up to zero.
Okay.
Sorry, I wasn't listening for a second. That center momentum frame, doesn't have anything to do with the problem, right?
No, it does.
It does.
That's what we're doing. That's what we're going to do instead of the lab frame.
Or at least we have that option, yeah. So this is still problem 7, right?
But I thought that the...
Yeah.
Oh, they have... Might give me a sec. Okay. I'm good.
Okay. So we do have the option of working in any of those frames. One thing that I would say is kind of a good way of laying out possible strategies is I could write down what do I know about my energy momentum 4 vector both before and after the collision, and if I haven't yet decided which frame I want to use, or maybe I want to use an interesting combination of both, what does the energy momentum 4 vector look like written with respect to the lab frame? What does it look like written with respect to the center of mass frame? So if I was going to do this, my energy momentum in here I could say, okay, I don't know that initial energy. I do know that it will be the square root of big M squared plus P squared. So I've got that. But I don't know its value. I don't know the value for Px. I don't know the value for Py. So those are all kind of independent, except that I know that B naught squared equals M squared plus Px squared plus Py squared plus Bz squared if it existed in here. Okay, after the collision, what do I know? Or after the decay, rather, what do I know? I've got a total energy that's E1 plus E2. These guys independently each have their own energy. And I can say I know that E1 squared equals M1 squared. This was big M plus P1 squared, and so on. I've got a total momentum. Well, the x component of my momentum is positive P2, and the y component is positive P1. And those are known quantities. So I know P1, I know P2, I know M1, I know M2. What are my unknown quantities? I don't know big M, and I would say I don't know any of the other energies and momenta that I've named that are not on this list. And what equations could I write? Well, by momentum conservation, each of these each of these components, there's the word I was looking for, each of these components must be equal both before and after the collision. So I can find, oh yeah, this tells me Px before the collision. It's actually just the same thing as P2. Py before the collision is the same thing as P1. Now, this is something where, you'd say, hey, they gave us a real kind of labor saver there by having those particles go out along nicely defined axes. Normally, I'd be saying px is p2 cos of blah plus p1 cos of other blah, and so on. So, you'd say, okay, that's kind of nice. That's something that's not going to happen every time. And I also know that original E naught has to be the same thing as E1 plus E2. Now, what does this give me? Well, I could say, instead of treating E naught and E1 and E2 like they were additional fundamental unknowns, I could say, let me relate them to the momenta, treat the momenta as my basic variables. So I'd say, okay, E naught is the same thing as square root of big M squared plus P1 squared plus P2 squared. E1 is the square root of 1 squared plus P1 squared. And E2 is the square root of 2 squared plus P2 squared. Now, how many unknowns do I have there?
3, 4.
I'm counting more optimistic than that.
So we know
2.
P1 and 2 and 1 and 2. We don't know big N. So that's 1%.
Yeah, so I should be able to solve that for big M.
Okay. Yeah, I got it.
So for this particular problem, working in the lab frame is probably worthwhile, just because with the mix of knowns and unknowns that they gave me, and the fact that, hey, they gave me a really nice gift. The fact that those momenta were lined up on the coordinate axes, but that's a gift that only applies in the lab frame. It doesn't necessarily apply in the center of mass frame. So in this case, the lab frame might be the way to go.
Because once we know big N, because we're trying to find its speed, and because we know its momentum, that's not hard.
Yes, exactly.